Okay, so we're covering 4-4 today in probability. The key concepts here are going to be basic multiplication rule. Basic multiplication rule is used when we have an AND situation going on. The last time we met was an OR, and with OR we do addition. AND is multiplication. Okay, so whenever you see that word OR, you're going to add. When you ever see that word AND, you're going to be doing multiplication. Most of the time they're going to be that the second trial is dependent on the first trial. Sometimes they're both going to be independent. So what do I mean by that? We talked a lot about births of boys and girls and babies. So a couple has a first child. It's a girl. When they get ready to have and they're having their second child, having that first girl has nothing to do with the sex of the second child. They are independent events. Okay? A dependent event would be, let's say that you are selecting a card from a full deck of cards. How many cards in a full deck of cards? 52. How many suits do you have? How many different suits? 4 different suits. What are they? Diamonds, spades, hearts, and clubs. Okay? And say that I wanted you to randomly select one card from that deck of cards, and I want to know the probability of getting, a club and a club. Excuse me. So, if I've got all 52 cards, right now, being that there's 52 cards, that means that I have 13 clubs, don't I? So my probability of drawing one club would be 13 out of 52. But now I have to draw a second card. That is dependent because I didn't put the first card back in. How many cards are left in that deck? 51. How many clubs are left? 12. So drawing a club and a club without replacement means that the second one is dependent on the first event. Okay? So the notation here, just so you know that, is the probability of A and B. It's the probability of the event A occurs in the first trial, and the probability of event B occurs in the second trial, just like we did when we took the first card, then we took the second card. The probability B/A is that the probability of event B occurring after event A has occurred. The probability that event B occurs after event A. So if event A had been drawing a club, we know that probability was 13 out of 52, but the probability that drawing a second club, given that a first club was drawn, is different. It's 12 out of 51. So that's what that means. The probability of event B, given that the event A has already occurred. That's the formal multiplication rule. Event A is going to occur, multiplied by, because it's AND. B is going to occur after I've already gotten A to occur. That's what that means. So if we were going to do that probability for my deck of cards, the probability of a club and a club, that would equal the probability of a club multiplied by the probability of a club given I already have a club. So the very first event we already said was going to be 13 clubs out of a total of 52 cards. So now that's my probability of the first event. Then I need to multiply because it's an AND situation. And I'm going to multiply by, hey, now that I have A that has occurred, I got a club, what's the probability of drawing the second club? 12 out of 51, because I only have 12 clubs left, and I only have 51 cards left. So somebody's going to do that multiplication for me. $117 out of? Oh, you already reduced it and everything. Okay? So probability of an AND situation, and I have a given. So intuitively is what we talked about at the very beginning. You guys already knew when I talked you through drawing those cards, you realized what was happening. I didn't really need my formula, but my formula was there to guide me. Hey, what's the probability of the first one? And means multiply. What's the probability of the next event? Always make sure when you're deciding how to do these, if the events are independent or dependent. The card was a dependent, wasn't it? So, an example of an independent event what is the probability of rolling a 6 when I roll a dice and then rolling a 6 again? 1/6 and 1/6. Exactly. Because how many sides are on a die? 6. How many times is 6 on that die? 1. So it would be 1/6. That second roll, when I roll it again, does that have anything to do with what I got the first time? Nothing. Absolutely nothing. So it's going to be multiply by 1/6. So my probability of rolling a 6 and then rolling another 6 is 1/36. Okay? Difference between independent and dependent events. And again, it's reiterated here, the occurrence of one does or does not affect the outcome of the other. Independent and dependent. Dependent events, we showed you how to calculate those, but here's a guideline. Because some of our calculations, when we get into big numbers, can become very cumbersome. Say that I wanted to pick randomly a female out of the student population at Delaware Tech. And the second time I wanted to choose another female out of the population of the students at Delaware Tech. So we have close to 13,000 students. Okay? So if I were to say I had 13,926 students, of which 8,120, I'm making up these numbers, 8,122 were female, that would be my first, right? Then I'd have to multiply by, and then I'd have to deduct one. It gets very cumbersome when you have to do multiple events. So our guideline is if that sample size is no more than 5% of the size of the population. I'm only picking 2 girls out of 13,000. That's certainly less than 5%, isn't it? Because of that, I'm going to treat them as if they are independent events. So all I have to do is take the 8,293 out of 12,893 and square it, because I'm choosing 2. I don't have to do this calculation, then the next, then the next, then the next. Do you want me to write that down so you make sense? Okay. There's one there in there. I don't want to give the homework away, though.
Oh, yeah.
Yeah. You just are so ahead. Good for you.
I thought we had to have it done. That's the only reason why. But it's not on this week.
But see, you should have said, yes, I did. Great job, and I'm ahead. Instead of qualifying. Okay, so if I said, choose one female and one female from our student population, and again, I'm going to make up these numbers, they really are dependent events, because I'm not going to put the female back in to be able to choose her again. Okay, so it would be 8,219 over 12,893. That would be the first probability. And if I did it by the hard, fast rule that says they are dependent events, because they are dependent events, I would then have to say multiply by 8,218 times 12,892, and if I had to do 5 of them, you'd see how cumbersome that would become, correct? Ugh. So instead, this rule takes over. And it says if the sample size is no more than 5%. What's my sample size? 2 females out of the entire student body at Delaware Tech. Well, that's a lot less than 5%, isn't it? So therefore, I can use it as though it's an independent event, and I can just say 8219 over 12893. How many am I choosing? 2. And if it said I was going to do a female and a female and a female and a female and a female 5 times, all I'd have to do is raise it to the 5th power. So it makes those calculations easier, and your difference between the two is going to be so minute, it's not going to matter.
And something that I want to comment on, because I know with me sometimes I'm unsure of how much 5% or 2% of the actual number is. The way that you would do it is you just take that bottom number, the 12,893, and you would multiply by 0.05.
Correct.
And I'm not sure exactly what that would get you, but then you would just take the, that would get you whatever 2% in this case is, and then you would do the less than or greater than sign, and I'm trying to think, I guess it would be 2, I think.
Okay.
You get what I'm saying?
Yes, I do. So, perfect. And I love the input. Keep giving me that input. So if I wanted to check to see if I could use this rule, what I would do is take 12,893, because that's how big my population is, and multiply that by 0.05. Somebody do that for me, because that's 5%, right? That's 5%. So if the sample that I'm pulling is less than 645 people, I can use this rule. Does that make sense? Correct. So if my sample that I wanted to choose 791 females, boy, what a calculation that would be, but that's what I would have to do. If I ever was pulling 644 girls, I can use this rule, and this would just be 644.
And hopefully Ms. Littleton will give us a rule, give us a problem that we can do.
It's going to be obvious. It's going to be obvious. Okay? Well, because this was choose one and choose one. But if I said choose 5 females, then it would be to the 5th power. If I said choose 644 females, it would be to the 644th power. Your calculators won't even be able to handle that. It'll go, no! And it'll just say error. Okay? All right. Does that make sense? But that's how I'm going to figure out if the sample I'm pulling is small enough from the population to be able to use that rule. Okay? Excellent. So here we are back to the drug users. Okay? And this is where it's reading. It's reading, it's reading, it's reading. Suppose 50 drug test results are given from people who use drugs. And there's my results. If 2 of the 50 subjects are randomly selected without replacement, find the probability that the first person tested positive and the second person tested negative. Okay? So right now we're already given that the person uses drugs. Everybody that was tested used drugs. How many total people were tested? 50. Of those people, how many had positive results and negative results? They are independent events, aren't they? Because I'm going to choose a person, and I'm not going to put them back in because it said without replacement. Then I'm going to choose a second person. Okay? So the first time, I want the probability that the person is positive. And if I were going to write it using my formula, remember that formula, to me it just makes sense not to use the formula, but I'll write it. Tested positive, it would be the probability of being positive. That's how I would write that. Then the second person being tested negative. I have to write that with the given statement. I have to say the probability of negative given my first person was positive. That's what all that means. But to me, that intuition means more. And we know that and means I have to multiply. So, looking at my numbers there, my results, the probability of choosing someone that's positive is 44 out of 50, and we can reduce that, of course. Now that I've taken one of those 44 out of one of those 50, now how many tests do I have left? I have one less because I took one person away, so my denominator is going to be 49. Did I choose a person that was negative before? No, I chose a person that was positive before, so my numerator is going to be what? 6. I hear everybody calculating. The first thing I would do would be reduce the fraction, make it easy. This can go down to 22 over 25, so at least that makes it a little easier, right? So 22 times 6 and 25 times 49 is 108 over. Yeah, okay, give me the fraction so that we have each step. What's 22 times 6? 132. And what is 25 times 49? And if I want to put that in a decimal, I'm going to round it to 3 significant figures, correct? And it's going to be 108. Zero eight. Does that make sense? Reading the chart. We'll have more of those, believe me.
Now, if we see that on like a test, do we have to do it with the fractions and the decimals, or can we just use the decimals?
You can just use the decimal. You don't need to you don't need to write the formula down. If it makes better sense to you just to think it out, I'm so in favor of that. You will be given the formula sheets on the test, though, just to, if you need them. Because this isn't a class on memorizing, right? It's a class on understanding and a class on being able to execute. Okay. So this one I bring to your attention because it is different, and it's a thinking problem. Very much a thinking problem. So when 2 different people are randomly selected from those in your class, find the indicated probability by assuming birthdays occur on the same day of the week with equal frequency. That means there's as many people that are born as Monday as there are on Tuesday, as there are on Wednesday, as there are on Thursdays, etc. Okay? I wonder if that's different. I bet it's different when there's a full moon at the at the hospital. I mean, seriously. Hospitals are crazy during full moons. Cindy is not here today, so I can't get her opinion on that. So the first one is the probability that 2 people are born on the same day of the week. Now, before we start to answer that one, the second one says the probability that 2 people are both born on Monday. They are different. The first one, the probability that 2 people are born on the same day of the week. Did I name the day of the week? Could it be Saturday? Could it be Monday? Could it be Sunday? I'll take the 2 Aarons. Aaron, what day were you born on? You don't know. Pick a day, your favorite day. Friday. Was there any probability of Aaron? She was just born on that day, wasn't she? I was only talking to Aaron. But now that Aaron has said Friday, the second person, Aaron, just because you're on opposite corners and you're both Aaron. Now Aaron's birthday, being on the same day as this Aaron's birthday, is what? How many days of the week are there? So, 1/7. Because I didn't specify what day of the week at first. Anybody could be it. So really the given part was after I chose one person, and the day was then stated. So that is 1/7. Which is different than Part B. Because Part B is the probability that two people are both born on Monday. So right now, before I even choose the first person, that first person I choose, what is the probability that they are born on Monday? 1/7. So that's my first person. That's my first person that I'm choosing. When I choose the second person, is that independent or dependent? Independent, because it doesn't matter what day my birthday was on. It didn't change what your birthday's on, right? So when I choose the second person, what is the probability? 1/7. So it would be 1/49. So that's a good thinking problem, to have you be thinking about what you're actually doing. Okay? Hmm?
So it's like, I'm getting kind of confused with independent and dependent. So would like dependent be like if you don't put, like, you know how you do the card they use like replacement? Would that kind of be like independent?
Yes.
And then just dependent if they're not putting in the card.
Absolutely correct. So just so everybody heard what Jemiah said was that the difference between independent and dependent. If you are drawing cards, and the first one you draw, you put the card back in. How many cards are you drawing from now? 52. So the second draw was independent of the first draw. But if I remove a card, and I don't replace it, I don't put it back in the deck, I change now my probability, don't I? So they would be considered dependent events. Very good. Very good. So we mentioned tree diagrams the other day. So formally, here it is. It's a tree diagram, which is a picture representation of what the probability outcomes can be. It can help you decide on the possible outcomes in a sample space. So here's an example. This one is, what is the probability of getting both questions correct? And this is assuming you don't know the answers. For instance, I could say, my second son was born on, what's today? September 13th. You do not have a clue if that's true or false, do you? So that would be a total guess, wouldn't it? So your probability of getting that answer correct is 1/2, right? 1/2. So it's true or it's false. How many possible outcomes did I have? I had 2. So then my next question, which is 5 possible multiple choice, I could say, my daughter was born in the month of January, February, March, April, or May. You don't have a clue, nor would you care. What is the probability that you would guess which of those months? 1 out of 5, because you had 5 possible choices. So the first question I had 2 choices. The second question I had 5 choices. So my total possible sample space, total possible number of outcomes, is 2 times 5 for a total of 10. And it will actually help me list every possibility. TA, TB, TC, TD, TE, etc., all the way down. Okay? So a quick summary there. The addition rule is an OR situation. Remember, in OR, we have to make sure we're not counting the same group twice. Remember, we took the highlighter and said, hey, it's this group, and where we overlapped, we made sure we didn't count them twice. And then the multiplication rule is the probability of event and another event, and we're going to multiply those together if they are independent events. If they're dependent, we have to do the probability of B given the first one happened. Okay? There's a little diagram to kind of sort it out. Probability of A and B, multiplication rule, because it says A. Are they independent? Yes, it's just the probability of A times the probability of B. Rolling a 6 and rolling a 6. No, drawing the cards. That's an example. The probability of A times the probability of B, given that A really did occur. Okay? So that leads us to our sample problems. Oh, I didn't talk about redundancy. So you know what redundancy means. And there's a great example in the book I'm going to go to, because it makes good sense. And this is what redundancy is. So, true story, independent jet engines, meaning I have jet engines on a jet, more than one. If one fails, it has nothing to do with the other one failing, does it? Okay, so they're independent events. So, soon after departing from the Miami Eastern Airlines flight number 855 had one engine shut down because of low pressure oil warning light. As the L-1011 jet turned to Miami for landing, the low pressure warning lights for the other two engines also flashed. Then an engine failed, followed by the failure of the last two working engines. The jet descended without any power from 13,000 feet to 4,000 feet. I'm getting chills just thinking of being on that plane. When the crew was suddenly able to restart one engine, and the 172 people on board landed safely. With independent jet engines, the probability of all three failing is only 0.0001 to the third power, because the probability of one failing by itself being an independent event, that means the probability of all three would equal the first one times the second one, running out of room, or I could just simply write to the third power. Independent events. And you can try to put that in your calculator, and when you do, you're going to get what's called scientific notation back. And you can try that. And it's going to say 1, 2 times 10 to the 9th?
Yeah, because I know you have a negative sign.
That's scientific. So that's a teeny tiny, itsy bitsy tiny little number, isn't it? Wow, how did that manage to happen? The probability of that is basically zero. I mean, we can hardly measure that. It is crazy. Well, let's go on to find out. That is really about 1 chance in a trillion. A trillion. The FAA found that the same mechanic who replaced the oil in all 3 engines failed to replace the oil plug sealing rings. The use of a single mechanic caused the operation of the engines to become dependent, a situation corrected now by requiring that the engines be serviced by different mechanics. So probability at work. Redundancy. Redundancy. Okay, bringing you to your problems to do.